a CNN, like with a different architecture, and we also started with GAN, which is the Generative Adversarial Network. All right, so GAN is the neural network that is used to train for image generation, not just image, but also text. You know, like when you have your chatbots and all those systems. So we have GAN network, which will help us with creating AI tools that will be used in those scenarios. Okay, so the generative adversarial network, which is a GAN, is just one of the most fascinating or powerful concepts of artificial intelligence, especially in deep learning and generative modeling. Okay, so GANs can generate new realistic data like images, music, or text, right? That are really similar to real world data. So GAN was introduced in 2014. So GAN is just so yesterday when we spoke about it, we mentioned the fact that GAN will have two parts. So GAN is composed of two neural networks that will compete with each other in a game-like setup. So you have the generator and the discriminator. So the generator will generate or create fake data. So, and then the discriminator will detect those fake data. So the generator creates fake data. So it basically takes random noise as input and generate data. So it can generate, like, for example, fake images. The goal is to fool the discriminator into thinking that its output is real. So the output of the generator needs to be introduced in the discriminator as an input, and the discriminator is going to detect if that was a fake data or it's a real data. So the discriminator takes both the real data that were available and the generated data as an input. All right. So the goal of the discriminator is to correctly distinguish real data from fake. So both networks are trained simultaneously in opposition. That's the reason why we use the term adversarial. Okay, so that's why we use the term adversarial. So the discriminator, the generator, is going to take as input. It's going to have the Gaussian noise vector. That means this will be the data that is going to take and generate images. So it's going to generate fake images. And this fake image that has been generated will be used as an input in a discriminator. So discriminator will take the real data that you provided and the fake data that was generated by the generator. And then it's going to determine if this fake image, it's going to distinguish the fake from the real. All right. So the output of the discriminator will be a probability that the given image are real or false. So that's the probability. That's the provided email are real. So that's how the GAN will work. So there's many ways of there's different ways of training that. So the way the discriminator is trained is not the same way as the generator. So you need to understand that how this is going to work is that the generator will produce fake samples from random noise, like fake images, fake faces, depending on what you're dealing with. And then the discriminator receive both the real sample from the data set and the fake samples from the generator. And then the discriminator learns to tell real from fake. So the generator learns to improve by trying to fool the discriminator, while the discriminator learns to tell real from fake. So this continue until the generator's output becomes so realistic that the discriminator can't easily tell the difference. Right, so that's how the training process is going to happen. So the analogy of this for you to remember easily is that when you think of GAN training like counterfeit money scenarios, right? So the generator is like a counterfeiter or person making fake money, and then the discriminator is a police officer trying to detect fakes. Okay, so both get better over time. The counterfeiter makes more realistic money, and the officer becomes a better detective. So eventually, the fake become close to the real one. So that's exactly how the GAN neural network will work. So you need to understand that the GAN will be composed of two neural networks, the discriminator and the generator. So the application scenarios of GAN you have, for example, in image generation, where we create human faces, landscape, or art, like all these images that you are seeing nowadays of people, but it wasn't them, and then people will be like, no, this is AI and everything. All these images we're seeing today, videos, music, generating music based on your on a prompt, and all those things, these are done by GAN algorithm. So okay, you have, for example, in cases where like converting sketches to photos, you have your super resolution, for example, to enhance low resolution images to high resolution. Data augmentation, that means you generate synthetic data from training AI models. Style transfer, which means apply artistic styles to images. So all these scenarios are example of GAN. So we have many types of GAN algorithm that come, because there have been a few variations. For example, you have the DC GAN, which we're going to talk about. The DC GAN is basically a deep convolutional GAN, which is used as convolutional layers for image generation. You also have the conditional GAN, which is the C GAN, which will generate data based on condition. Example, your class labels, you understand? So you have other type of GAN, like cycle GAN, which will translate images between two domains. For example, an image from like the horse to the zebra, things like that. So you need to understand that training again network will be done differently. So you don't train a discriminator as you train the generator. So the discriminator, the way you train a discriminator is that remember, just for you to remember first that the discriminator is basically a binary classifier, which means that it's gonna try to determine between real samples and fake samples. So we have real samples and fake samples that were generated by the generator. All right, so this too, so it's that's why we're calling it a binary classifier, because it needs to determine between real and fake. All right, so now this is maybe the image of a cat, and this is the fake image that was generated by the generator. So the image that was produced by the generator is the fake one. So the discriminator will output the probability between 0 and 1, where 1 means real, 0 means fake. So the closer it is to 0, the image will be determined as fake. The closer it is to 1, it is real. So when you're training the discriminator, the steps will be that we will have to train on real data. So we actually take a batch of real images from the data set, and then you feed them into the discriminator. You label them as real. All right, so that's how you're going to do, because these are real world images. So you need to label them as real to tell the discriminator that these data are real. And then the discriminator will adjust its weight to output value close to 1 for these images. And then the step 2 will be to train on fake data. So to train on fake data, you're going to take a batch of random noise vectors. That's example like 100 dimensional random numbers. All right. So you pass them through the generator, and then it outputs fake images. And then you feed these fake images into the discriminator. So the image released from the generator will be taken as sample in the discriminator. So we feed them to the discriminator, and then we label them as fake 0. So the discriminator will now know these are fake. So now the discriminator will adjust its weight output values close to 0 to say this is fake, right? And then now the discriminator will have to create the loss function. And the loss function, the discriminator's goal is to just maximize the accuracy. So it wants to correctly classify real as 1 and fake as 0. So the loss function is usually it's a binary cross entropy function. So the binary cross entropy function will be used as a loss function, and that's how the model is going to be used. So the discriminator will be updating the weight by minimizing the loss function. So as we've seen it in AI, when we talk about the loss function, all right, so the loss function, in this case, we're going to use a binary cross entropy. So that loss function is going to reduce the to be used for the discriminator. So the key idea so is that during the training, the discriminator will learn to be better detector of fake. The generator learns to produce better fakes to fool the discriminator. So, but the discriminator will learn to better detect that. All right, so we're going to have another way. So, but it's very important to note that training the generator will now be different. All right, so remember the generator needs to learn how to fool the discriminator. So to train the generator, the goal of training the generator is to fool the discriminator so that the discriminator cannot distinguish between real and fake images. So in this case, remember the real images, the probability must give us 1, and the fake, the probability must give us a number that is close to 0. So when we're training a generator, the generator will try and create fake data, like fake images, right? That looks so realistic that the discriminator makes mistakes while trying to distinguish them. So the discriminator can mistaken them for real. So it doesn't see real images. It learns only from the feedback gradient that it's received from the discriminator. So that feedback from the discriminator help the generator create these fake images, because the more the discriminator is becoming more accurate, the loss is being reduced here. The generator tries to fool it more. That's how it works. So basically, the generator goal, which is to fool the discriminator, so we're going to have a loss function, a different loss function that is going to be used for for training the generator. So so the training steps will be: we generate fake data. So take a batch of random noise vector, pass them through the generator to get the fake images, and then evaluate fake images. So by feeding those images to the discriminator, so the discriminator gets these images, which should be close um, to one. Remember, one means real. So this prediction must be close to one. That means the discriminator thought this was a real image and classified it as a one, as a real, while it was a generated image from here. So if these images are not being generated, are not classified as real, the generator will try and generate other images to fool the discriminator, because that's the purpose. So, um, so to evaluate the fake image that was generated, or the sample, will be inserted into the discriminator, which should be close to one if the generator fooled it. All right. So, and then we're gonna compute the generator loss. So compute the generator loss using the discriminator's output, but pretend the fake images are real. So this will train the generator to produce images that makes that prediction real. So it keeps producing real even if the images uh, are, are fake. And then we use back propagation algorithm to generate a way to try and recreate that. So we compute gradients through the discriminator, but only update the generator's parameters. Okay. And then the discriminator's weights are frozen in this step. So we have the weight that are frozen here. So we're not changing anything on the discriminator. We keep it the way it was trained. And then the generator keep sending fake and trying to get them to trying to fool the discriminator. All right. So, so that's how the interaction between your generator and discriminator is that your your discriminator will try and classify real as one, fake as zero, and then we as doing that, the generator keep providing the pictures, and then this generator on its side, when it's being trained, it needs to fool the discriminator. So it needs to classify fake images as real to show that the generator is doing a good job. All right. So we're going to have that. But when training a GAN network, we may have also a problem of underfitting and overfitting, just like we can have it with other neural networks. So when we have a problem of overfitting or underfitting, we need to solve it by either increasing the numbers of hidden layers, or we can also introduce other structures such as your DC GAN, which is a deep convolutional generative adversarial network, which is a type of GAN which use a different structure. All right, so overfitting, we solve overfitting the same way we can solve overfitting with other neural network by using techniques such as dropout and other technique like increasing the size of data set. All right, so another problem that we, apart from overfitting and underfitting, another problem we can have with GAN training is the mode collapse. All right, so the mode collapse is one of the unique, is one of the problem that we only find when we're dealing with GAN. Okay, so what is the mode collapse? So it's basically an effect or something that happen when the generator stops producing diverse outputs. So when the generator, now it's trying to generate these fake images, but it's keep generating only a few kind of samples, even though the real data has many variations. So the real data, there's many variation. Maybe you have pictures of, let's say, pictures of cats. You have cats in different positions, cats in different sizes, and all those. Those are the data. But now your generator is only producing one type of cats. So it's not creating the fake images of different type, but it's only creating a certain type. So that is what we call the mode collapse. So instead of producing diverse output, it only generates only a few kind of samples, even though the real data has many variations. So in other words, the generator collapsed to a small number of modes, like a pattern or style of the data distribution. So for example, suppose you are training a GAN to generate handwriting digits, like from 0 to 9. Then you are using, let's say you are using the MNIST data set. So the aim is to generate these images, digits from 0 to 9. So now the generator, instead of generating fake images of 0, 5, and other numbers, now it only generates fake images of 1. You understand? Simple thing like 1, 7, and it's avoiding things like 8. So you now having a problem where the generator is supposed to learn to produce all digits 0 to 9. But in mode collapse, it might only generate 3s and 7s because those are maybe easy to fool the discriminator. So instead of learning the whole distribution, it learns only a few modes of it. So why does mode collapse happen? So um, this issue, which at the moment remain unresolved, this issue occurs because of the adversarial feedback loop between the generator and the discriminator. So you have the generator that finds one pattern, which is a few outputs that fools the discriminator perfectly. Now the generator is so happy that it was able to fool the discriminator, but it forgets the variation between the data. Now it only focuses on that type of data that was able to fool. So now the discriminator gets confused and starts labeling few fake samples as real. So now the generator keeps producing the same type of output because it gets a low loss and a good reward for doing that. Now, over time, the generator stopped exploring other opportunities. So it only focused on what was producing good results. So this feedback loop makes the GAN unstable and less diverse. Okay, um, so to think of it in visual understanding, so let's imagine a real data set with 3 clusters. So we have like A, B, and C. So a well-trained generator should create samples in all 3 clusters. But in mode collapse, the generator might only produce samples around cluster A. So now we have real data distribution, which was supposed to be A, B, and C, but now the generator output is only A. So even though the samples look realistic, they don't represent the full diversity of the real data. So now this issue is still what you call that. This issue is still unresolved, but fortunately, many research papers have proposed various methods to mitigate it, such as using other type of GAN structure like the VGAN, other GAN, MADGAN. So there is many other uh, type of what you call this of structure that can solve this problem. All right. Uh, another problem that we may have is what we call instability. So the instability is created by a vanishing gradient. All right, so which means that when GAN training is just starting, we may have vanishing gradient. All right, so vanishing gradient, remember we spoke about it in different um, neural network where we've mentioned that because the neural network, as the more layers we have, the more we are losing the values of all the numbers that we're having. So we have a vanishing gradient. So um, uh, so when we talk about vanishing gradient, um, in GAN, it's basically when you look at the generator that learns by receiving gradient from discriminator. So the discriminator's information are coming back to the generator as data, and that's how the generator keeps learning. But these gradients tell the generator how to adjust its weight, all the weight, in order to produce more realistic data. So if the gradient becomes very small, very close to zero, then the generator stops learning. So now we're having a vanishing gradient problem. So a vanishing gradient occur when the discriminator becomes too good at distinguishing real and fake samples too early in the training. So we were supposed to be training for a long time, but too early in the training, the discriminator become too good. So that creates a vanishing gradient problem. So the discriminator will just output 1 for real and 0 for fake. So now the discriminator keep putting 1, 1, 1. So now the result is that the generator stop learning, and then the GAN training gets stuck. So this can be a problem and create the whole instability. All right. So so when you think of it, if we have to think of it in an intuitive, in a different analogy, you think of, like, imagine a teacher which can be classified as a discriminator, who's like a teacher who's too strict. So now the student, who's the generator, uh, turns in a bad essay. Now the teacher immediately gives 0 out of 10 without saying why. Now the student gets no useful feedback to improve, but they just got 0 out of 10. So even if you ask that student to come back with a different essay, they don't know. There's no feedback because the teacher was too strict and gave them a 0 out of 10. So there's no way the student can improve themselves. So that is an example of vanishing gradient. So what happened is that the teacher's feedback is too harsh that learning stop. There's no way you can learn from it. All right. So that is so how to fix the issue of vanishing gradient is by using different structures of GAN, such as the W GAN, the LS GAN. So these are type of GAN that have a different type of loss function, and that will solve the issue, right? So so the instability is created by a vanishing gradient or a poor convergence. So yeah, a poor convergence can also create an instability in that. So when we're trying to mitigate these training instabilities, we can use 2 techniques. We can use a single-sided level smoothing or a separated batch real and generated images. And then we can use different structures such as the DC GAN. So the DC GAN is the deep convolutional generative adversarial network. So the deep convolutional GAN is just one of the most important and influential architecture in the evolution of GAN, right? So the DC GAN is just a type of GAN that uses convolutional neural network. like CNN, instead of a fully connected network for both the generator and the discriminator. So this structure or this architecture was introduced in 2016, right? So that is the main motivation behind that was before the DC GAN, like when you think of early GANs, they were just using fully connected or dense layers, fully connected layers, which didn't work well for images, you understand? So they were unstable and produced low quality output. But the DC GAN introduced convolutional and transport convolutional layers, which is leading to better image quality being generated, more stable training, uh, and then a strong automatic feature learning. Okay, all right. So this is the structure when you think of the structure of this architecture here of the DC GAN. So basically, the DC GAN is going to use transpose convolutional network. So uh, we're going to have like an input. The first input will be maybe remember the generator supposed to input only the random noise. But when we look at this, the DC GAN, so the DC GAN will have the input, which will be the random noise, and then it's going to have hidden layers. So the hidden will be like a transpose convolutional, um, uh, and then the output will be the transport convolutional and another activation function. That's how it's going to be able to generate the images, right? And then in the discriminator as well, we're going to have convolutional layers to try and complete that. All right. So there's an introduction of convolutional kernels that we've seen the same way we've seen it on in CNN. So um, so to for this discriminator to actually perform the whole classification task, so we can construct the discriminator in a DC GAN similar to the other convolutional neural networks such as the LNet, the LINET, right? So this will perform a binary classification to just generate the real images using convolutional pooling. Remember when we spoke about CNN? So we're going to have a pooling layer where we can have maybe, if we're using pooling in this case, maybe we're looking for an average. So the kernel, if we have a kernel, a 3x3 kernel here, so the 3x3 kernel will take everything in this area and then do the calculation to produce a feature map, which is a feature map after the transpose convolutional. Okay, so that's how we're going to actually deal with that in a DC GAN. So the strength of the DC GAN, is just that it's going to produce high quality images compared to the normal GAN, early GANs, right? So you have a stable training because of what we call the batch norm and the CNN structure that has been introduced. So it's going to learn useful features automatically, right? Yeah. But the limitation of this is it's still vulnerable to mode collapse. And then you have a limited to low resolution images, such as the 64 by 64 and then there's also a training instability. If the upper parameters are not tuned properly, you can also have a training stability there. All right. So another architecture can be the CGAN. The CGAN is the conditional generative adversarial network. So the CGAN will be just another structure. So the CGAN is just an extension of the GAN that will allow control or guided image generation by just providing extra information conditions to both the generator and the discriminator. So the main concept here is that when you think of it in a regular GAN, the generator produces random output from random noise, right? With no control over what it's generated. So in this case, we are kind of trying to control the type of data that needs to be generated. So in the CGAN, the model is trained with conditions such as labels. So we have class information, text description. We have certain attributes that can be like the color, type, shape, everything. So when generating data, you can tell the machine to generate certain type of data. So that's how what you call this, the CGAN will work. It will work with conditions. So by conditioning on this information, the CGAN can generate specific type of images. For example, images of a digit 5 or faces with smiling expressions. So we tell which type of image we need. All right. So so what will happen? Remember the generator. The generator should have just have the noise, right? Which is the random noise vector Z, right? And we have, in this case, instead of, when you look at the normal GAN, we have the random noise that is given to the generator, and then we have the real images coming from the data set. So the generator will create the fake image. So the fake image that has been generated together with the real image will be introduced into the discriminator as an input, and the discriminator will give a probability to see if this image is real. All right. But now when we introduce the CGAN, in the CGAN structure now, here in the generator, we don't just have the random noise Z, but we also have a conditional label. So this conditional label Y is also an input. All right, so this conditional label Y is also an input. So this input is going to play together with the Z as an input to the generator for it to generate. So we've now given a conditional label there. So in this case now, the generator will generate an image that should match the condition Y. For example, if Y is a cat, is equal to cat, the generator tried to create a cat image. So that's the condition that was given. So the generator tried to create a cat image. And then in the other case now, the discriminator will receive the real, right? The real image and also the condition Y together. So it's going to learn to output one if the image is real and matches the label. It's going to output 0 if the image is fake and does not match the label. All right, so that's how the information will come. So in this case, we're going to have the label, condition, plus noise in the generator. The generator gives us the fake. Now we take the fake plus the condition here. And then here we take the real plus the condition and then introduce in the generator, and then the generator will give us the probability. So all right, so in this case now, we just added this conditional. So that's why we call it the conditional GAN. All right, so all right, so this is used in the cases where we're going to use this in applications such as image generation by class. where we generate maybe digits. We give a condition that it needs to be from this number to this number. You have maybe to convert like an image to image translation, where you can convert sketches like photos from the day, photos in the day to night. So you have those conditions that you have on the data. So some of the advantage of this is that it gives you control over the type of images that are being generated. It's reduced randomness of that you have in a standard scan. So this is useful for supervised and semi-supervised tasks. All right, so obviously it's going to improve the training stability. All right, guys, so that's all for today. Any question before we can call it a day?
So do you know this? I think it's an open AI called Sora.
All right, guys. Thank you. I will see you tomorrow. Have a great evening.
Sir.